Deep in a laboratory beneath Switzerland, scientists trapped 100 atoms of anti-helium for 3/millionths of a second before they vanished. This substance costs more than $60 trillion per gram. It annihilates on contact with anything. We are about to explore the rarest materials in existence, from elements that self-destruct through heat to stars made of quarks that could convert your body into strange matter instantly, to black holes smaller than atoms that explode with the power of nuclear bombs. If you enjoy discovering what hides in the darkest corners of reality, prepare yourselves. We begin. Every particle you see has an evil twin lurking in physics equations. Scientists call this antimatter. When physicists first predicted it in 1928, the equations showed something impossible. Particles with identical mass, yet opposite electric properties. 3 years later, cosmic rays proved the theory correct. Antimatter behaves like a photograph negative of reality. Where normal matter has negative electrons, antimatter contains positive ones called positrons. Where atoms have positive protons, anti-atoms contain negative antiprotons. The masses stay identical, only the charges flip. Here comes the terrifying part. Touch antimatter to normal matter, and both explode instantly. The collision converts their entire mass directly into pure energy. Following Einstein's famous equation, no chemical reaction comes close to this efficiency. Nuclear bombs release less than 1% of their fuel as energy. Antimatter converts 100%. Picture holding 1 gram of antimatter. Scientists confirmed this would release energy equal to 43,000 tons of explosives, the blast from 2 atomic bombs from something weighing less than a sugar packet. Nature produces tiny amounts through specific processes. Lightning storms create positrons above thunderclouds. The radiation belts around Earth trap small quantities of antiprotons. High-energy collisions in deep space generate antimatter particles constantly. Yet, something happened early in cosmic history that remains unexplained. Theory suggests the Big Bang created equal amounts of matter and antimatter. Both should have annihilated completely, leaving only energy. Instead, a tiny imbalance occurred. For every billion antimatter particles, there existed 1 billion and 1 matter particles. That single extra particle in every billion became everything we see today. The missing antimatter ranks among science's deepest mysteries. Where did it go? Why did matter win? Some unknown process during the first second of existence tipped the scales. Physicists call this the baryon asymmetry problem. Today, antimatter exists as the rarest substance scientists can study. The largest particle accelerator on Earth produces about 1/billionth of a gram per year. Creating just 1 gram would require running that machine continuously for 1 billion years. Storage presents another nightmare. Antimatter cannot touch any container wall. Any contact means instant annihilation. Scientists use powerful magnetic fields to levitate individual antiparticles in perfect vacuum chambers. Even then, storage times measure in minutes before the particles escape and explode. What happens when researchers finally captured enough antimatter to test directly makes the impossible seem possible. In 2011, researchers at Europe's Particle Physics Laboratory achieved something that should not exist. They created anti-atoms of helium, not individual antiparticles, but complete anti-atoms with structure and stability. Normal helium has 2 protons and 2 neutrons at its center, surrounded by 2 electrons. The anti-helium these scientists built contained 2 antiprotons and 2 antineutrons orbited by 2 positrons, a perfect mirror image of regular helium. The difficulty of this accomplishment defies imagination. You must smash particles together at speeds approaching light velocity. Identify the few anti-helium atoms among billions of other collision products, and then trap them before they touch anything and vanish. The team succeeded in creating exactly 9 complete anti-helium atoms. They existed for 30 billionths of a second before hitting detector walls and exploding into radiation. These 9 atoms represented years of work by hundreds of scientists. Yet, this confirmed something extraordinary. Antimatter follows the same physical laws as normal matter. This means antimatter could theoretically form anti-stars and anti-galaxies somewhere in space. Astronomers search for such regions constantly. If antimatter galaxies existed, the boundary between matter and antimatter regions would produce constant gamma-ray explosions as particles from each side mixed and annihilated. So far, nothing confirmed. The entire observable universe appears built from normal matter. The cost of producing antimatter makes it simultaneously the most expensive and most worthless substance imaginable. Scientists estimate antihydrogen costs $62 trillion per gram, the entire economic output of 3 United States economies for 1 year. You cannot use it as fuel, because creating it requires pumping in exactly the same energy you get from annihilation. The containment systems weigh thousands of times more than any antimatter they could hold. Some researchers suggest antimatter could power deep space missions someday. The perfect efficiency of matter-antimatter annihilation would enable spacecraft to reach incredible velocities. But the practical problems of safe storage and control remain unsolved. The moment antimatter touches normal matter, physics enters its most violent mode. 2 particles meet. Both cease to exist. Energy erupts outward at light speed. This process operates fundamentally differently from any chemical reaction or nuclear process we know. Antimatter annihilation converts everything to energy. Scientists have measured this process precisely. 1 kilogram of antimatter meeting 1 kilogram of matter releases energy equivalent to 43 megatons of explosives, about 3,000 times more powerful than the bomb dropped on Hiroshima. The annihilation produces specific signatures. When an electron meets a positron, both vanish and emit 2 gamma-ray photons, flying away in opposite directions. Each photon carries exactly 511,000 electron volts of energy. This energy signature allows scientists to detect antimatter creation events. Thunderstorms produce detectable positron emissions. Even medical scanners use this effect deliberately. Positron emission tomography machines inject patients with radioactive tracers that emit positrons. The resulting gamma-ray pairs reveal metabolic activity inside organs and tumors. When heavier antimatter particles collide with their matter counterparts, the annihilation becomes more complex. Antiprotons, meeting protons, produce showers of other particles like pions and various mesons. The total energy released follows Einstein's equation precisely: mass multiplied by the speed of light squared. 1 gram of matter contains about 9 10 joules of energy. That equals 21,000 tons of TNT equivalent. 10 grams would release energy, matching the largest nuclear weapons ever tested. Nature demonstrates this power constantly on tiny scales. Cosmic rays slamming into atmospheric molecules create matter-antimatter pairs that immediately annihilate. The largest antimatter reserves in our solar system exist in radiation belts trapped by Earth's magnetic field. Satellites have detected antiprotons circling our planet at altitudes of several hundred miles. Scientists have captured and stored individual antiprotons for over 1 year in specialized magnetic traps, representing the longest any antimatter has existed in human custody. Scan the entire planet. Check every rock formation, every ocean bed, every mountain peak. Search all 6 million trillion pounds of Earth. You will find less than 1 ounce of a substance, so rare, scientists debate whether it even deserves study. Element 85 sits on the periodic table, marked At for astatine. The name comes from Greek, meaning unstable. That label undersells the reality by a massive degree. Astatine atoms cannot exist for more than a few hours before self-destructing. The most stable version, astatine 210, survives 8 hours on average before splitting apart. Most forms last mere seconds. This rapid decay means any astatine present when Earth formed has long since vanished. The tiny amounts existing today form continuously through radioactive decay chains, primarily as an intermediate step when uranium and thorium atoms break down. Scientists estimate roughly 25 grams spread across the entire planet at any moment. Scientists cannot collect natural astatine samples. By the time you identified where an atom formed, it has already decayed. Every study of astatine requires artificial production in particle accelerators. Researchers bombard bismuth metal with alpha particles, creating astatine atoms one at a time. The total amount of astatine produced by all laboratories throughout history adds up to less than 1/10,000,000th of a gram, about 500 nanograms. If you gathered every astatine atom ever created by humans into one place, it would be invisible, even under powerful microscopes. Why does astatine decay so rapidly? The nucleus contains 85 protons, crammed into a space smaller than an atom. That many positive charges repel each other with intense force. The strong nuclear force barely holds them together. Any tiny quantum fluctuation breaks the balance, and the atom flies apart. Nobody has ever seen pure astatine in elemental form. Theory suggests it would appear as a dark, possibly metallic solid at room temperature. But accumulating enough astatine to see creates an insurmountable problem. The intense radioactivity from even microscopic amounts would generate heat through particle emission. That heat would vaporize the sample instantly. Any visible quantity of astatine would literally boil itself into gas through its own radioactive decay. Some calculations estimate that assembling 1 microgram, 1/1,000,000th of a gram, would produce enough heat to immediately vaporize the sample and possibly damage surrounding equipment. The element earns the nickname "goodbye" for good reason. Despite existing in nearly unmeasurable quantities, astatine might become crucial for medicine. Certain isotopes emit alpha particles, a high-energy radiation excellent at destroying cancer cells while causing minimal damage to surrounding healthy tissue. Researchers test astatine 211 attached to antibodies that target tumors. The radiation acts like a microscopic bomb delivered directly to cancer cells. The 8-hour half-life gives doctors enough time to prepare and administer treatments before the astatine decays away. The challenge remains producing and transporting enough astatine from accelerators to hospitals before it vanishes. Astatine represents only the rarest naturally occurring element. Artificial elements achieve even greater rarity. Look at the periodic table. Count the elements from number 1 through number 94. Every single one appears naturally on Earth except one. Element 61 stands empty, a gap in nature's collection. Scientists named the missing element Promethium, after the Greek titan who stole fire from the gods. When researchers first assembled the periodic table, they noticed the missing element between neodymium and samarium. The reason eluded scientists for decades. Finally, in 1945, scientists at Oak Ridge National Laboratory created Promethium artificially by bombarding uranium with neutrons in a nuclear reactor. They isolated a sample and confirmed its properties matched predictions. The explanation for Promethium's absence became clear. all promethium isotopes are radioactive, with relatively short half-lives. The longest-lived version, promethium-145, survives about 18 years on average. Any promethium present when Earth formed decayed away billions of years ago. Today, promethium exists only through artificial production, or as an extremely rare byproduct of uranium decay. Scientists estimate perhaps 500 grams exist naturally across the entire planet at any moment. Total artificial promethium production since discovery amounts to less than 1 kilogram. Promethium glows in the dark, not through fluorescence, but because the radioactive decay itself excites electrons in surrounding material, making it emit blue-green light. This property led to early applications in luminous paint for watch dials and instrument panels. But safety concerns ended this use. The rarity of promethium creates strange situations in chemistry. Students learn about all elements through hands-on experiments, but promethium remains theoretical for nearly everyone. Even professional chemists rarely encounter it. Natural promethium production on Earth pales compared to stellar environments. Inside dying stars, promethium forms continuously through nuclear processes. Analyzing starlight sometimes reveals promethium's spectral lines, providing evidence of active nuclear reactions in stellar atmospheres. This connection between Earth's rarest elements and stellar processes hints at deeper connections. Everything heavier than hydrogen formed inside stars or during stellar explosions. The presence or absence of specific elements on Earth reveals our planet's nuclear heritage. These questions lead to even stranger possibilities. Could exotic matter exist with properties that make common elements seem abundant? Take a teaspoon, fill it with neutron star material, place it on a scale. The needle would read 4 billion tons. This weight would crush through the scale, through the floor, through the Earth's crust, and sink toward the planet's core. Neutron stars represent matter compressed beyond normal limits. When massive stars explode in supernovas, the cores that remain collapse under their own gravity. Atoms get crushed into oblivion. Electrons get forced into protons, creating neutrons. Those neutrons pack together so tightly that a city-sized sphere contains more mass than our entire home star. Picture compressing all of humanity, 8 billion people, into a space the size of a sugar cube that approaches neutron star density. Every cubic inch contains the mass of Mount Everest. The pressure inside these objects defies description. At the surface, gravity pulls with 100 billion times Earth's force. Mountains on neutron stars cannot rise more than a few millimeters before the gravity flattens them. Scientists believe the surface forms a crystalline lattice of iron nuclei, frozen into the hardest material in the universe. Below the crust exists an ocean of superfluid neutrons. These neutrons flow without friction, without viscosity, without any resistance. They form a quantum liquid that behaves unlike any normal fluid. Diving deeper reveals more extreme conditions. Neutrons pack so tightly they begin touching. Under neutron star pressures, the quarks inside those neutrons might break free from their confinement. This possibility leads to one of the strangest ideas in astrophysics. If pressures grow high enough to dissolve neutrons completely, the quarks might rearrange into different patterns, forming a quark liquid. Theory suggests this transition happens at about twice normal nuclear density. Many neutron stars likely reach these conditions at their cores. Observing neutron stars provides clues about their interiors. When neutron stars spin, they emit beams of radiation like cosmic lighthouses. These pulsars flash with incredible precision. The spin rates, gravitational effects, and cooling patterns all reveal information about internal structure. Recent observations detected neutron stars more massive than scientists predicted. The heaviest confirmed examples contain about twice the mass of our home star, compressed into a sphere 12 miles across. Their existence pushes models to extreme limits. These massive neutron stars might contain exotic forms of matter, stabilizing them against collapse. When two neutron stars collide, they create the most violent events in the cosmos. The collision melts both stars, sending shock waves through the neutron fluid. The merger might form a more massive neutron star, or collapse directly into a black hole. Gravitational wave detectors have captured signals from multiple neutron star mergers. By analyzing the signals, scientists can estimate how stiff or soft neutron star matter behaves. Current data suggests neutron star matter behaves stiffer than many models predicted, implying the strong nuclear force remains powerful, even at extreme densities. Everything around you is built from two types of quarks, up quarks and down quarks. These combine in threes to form protons and neutrons, generating every atom in existence. Nature actually provides 6 varieties of quarks. Up and down represent only the lightest pair. 4 heavier flavors exist with peculiar names: strange, charm, top, and bottom. These exotic quarks appear in high-energy physics experiments, then decay almost instantly into their lighter cousins. Strange quarks earn their name from their peculiar behavior when first discovered. A strange quark weighs about 30 times more than an up or down quark. This extra mass makes strange quarks unstable in normal conditions. Standard physics assumes strange quarks play no role in bulk matter. Then theorists asked a simple question: what if strange quarks could become stable under extreme pressure? At some point inside a neutron star, having a strange quark in a low-energy state costs less energy than having a down quark in a high-energy state. The strange quark becomes favorable. Instead of pure neutrons, the cores might contain free-floating quarks in a mixture of up, down, and strange varieties. Theory predicts this strange quark mixture could be stable, or even more stable than regular nuclear matter. If true, this strange quark mixture would have lower energy per particle than normal nuclei. It would represent matter in its true ground state. Everything we consider normal would actually be metastable, existing temporarily, because converting to strange matter requires extreme triggering conditions. The strong nuclear force that binds quarks together behaves differently when many quarks crowd into small volumes. Exotic quantum effects could lock strange quarks into stable configurations. The resulting matter would possess unprecedented density and strength. It would resist further compression. This could form self-bound objects held together by quark interactions rather than gravity. The sweet spot for these objects might span masses from about twice our home star up to 3 times that mass. Some observations hint at candidates in this mass range. The real test involves a much more radical prediction. What if strange matter can exist as independent objects? Imagine a droplet of liquid so dense a marble-sized sphere weighs more than Mount Everest. Now imagine this liquid can convert any normal matter it touches into more of itself. Finally, imagine that billions of these droplets might drift through space undetected. Scientists call these hypothetical objects strangelets. They represent fragments of strange quark matter, small enough to qualify as particles, yet large enough to contain millions or billions of quarks. Their size could range from atomic nuclei up to grains of sand. Larger fragments are called strange stars. If stable strangelets exist, their properties would be extraordinary. Unlike normal matter, strangelets would bind through the strong nuclear force acting directly between quarks. A strangelet the size of a virus might weigh as much as a small mountain. Detecting strangelets presents enormous challenges. If they move through space, they would resemble cosmic rays, but with extremely high mass-to-charge ratios. Some researchers searched for strangelets incorporated into Earth's matter. No confirmed strangelets have appeared. One controversial question involves whether strangelets might catalyze conversion of ordinary matter. Some models predict that a strangelet touching normal atomic nuclei could trigger a chain reaction. The process would repeat, converting everything it touches. If started on Earth, such a wave would convert the entire planet to strange matter in about 1/10 of a second. The process would release energy equivalent to countless nuclear bombs, but spread across the whole planetary volume. From outside, observers would see Earth's mass remain constant, while its radius shrinks to about 100 meters. Most physicists lean toward strange matter being unstable or only marginally stable. The entire observed universe suggests that ordinary matter maintains genuine stability. However, this does not prove strange matter cannot exist under specialized conditions, such as the cores of massive neutron stars. What happens when strange quarks dominate an entire stellar object reveals even more extreme possibilities. What if it represents the true ground state of all matter? The possibility of an entire star, made purely of strange quark matter, divides astrophysicists. If strange stars exist, they would appear different from neutron stars in subtle ways. Strange stars should have sharper edges than neutron stars. A strange star's density would drop nearly discontinuously, covered only by a thin layer of electrons. X-ray telescopes search for these signatures. Strange stars might form through a core collapse under just the right conditions, or from a neutron star converting over time. If a neutron star accretes enough material from a companion star, the added mass might push the core density past the threshold for strange matter formation. This conversion process should release enormous energy, producing a distinctive type of explosion. The conversion rate depends on how efficiently strange matter nucleates inside neutron stars. If strange stars do exist, their presence would revolutionize our understanding of matter under extreme conditions. It would confirm that quarks can exist in bulk outside normal particle confinement. But strange stars represent only one type of extreme stellar remnant. Others push the boundaries of physics in different directions. Earth has a magnetic field that measures about half a Gauss at the surface. Now, multiply that strength by 10,000 trillion. You reach magnetar territory. Magnetars are neutron stars with magnetic fields so powerful they warp the quantum vacuum itself. These fields reach 1 quadrillion Gauss at the surface. At a distance of 600 miles, a magnetar's field would erase every credit card on Earth. Only about 30 confirmed magnetars exist in our galaxy. They form when neutron stars are born, with extremely rapid rotation rates. The resulting magnetic field stores energy equivalent to the star's rotational energy, creating an unstable situation. When the field wants to reconfigure to lower energy states, the stored energy releases explosively. Magnetar flares are the most violent electromagnetic events in the universe, besides gamma-ray bursts. In less than a second, a magnetar can release more energy than our home star emits in 100,000 years. The magnetic fields create bizarre effects near magnetar surfaces. Light does not travel straight through such strong fields. Photons split into two polarization modes that propagate at different speeds. The crust of a magnetar experiences unimaginable stress. Magnetic pressure tries to expand the star outward. Gravity tries to compress it inward. Eventually, The crust cracks suddenly in a starquake, releasing stored elastic energy and generating a magnetar flare. The existence of magnetars proves that nature can create conditions more extreme than anything achievable in laboratories. Their magnetic fields exceed human technology by factors of trillions. They operate in regimes where quantum electrodynamics becomes nonlinear, and the vacuum itself gains properties. Yet even more exotic objects might exist. The first stars did not light up until about 100 million years after the Big Bang. Before stars existed, tiny black holes might have appeared. These primordial black holes did not form from stellar collapse. They condensed directly from density fluctuations in the extremely hot, dense early universe. The lightest primordial black holes would have been truly tiny. A black hole with the mass of Mount Everest would measure only 1 nanometer across. One with the mass of a large asteroid would be about the size of a proton. These microscopic black holes would be far smaller than atoms, yet contain more mass than mountains. Primordial black holes offer a possible explanation for dark matter. They gravitationally affect their surroundings identically to dark matter. They interact only through gravity. Testing this hypothesis involves gravitational microlensing, which can detect compact objects passing between Earth and distant stars. Current data suggests primordial black holes might account for a few % of dark matter at most. Something else must dominate. Another test involves gravitational waves from black hole mergers. When LIGO detected colliding black holes with unexpected masses, some researchers proposed they might be primordial rather than stellar in origin. Very small primordial black holes would have been extremely hot. Temperature increases inversely with mass for black holes. Microscopic black holes would radiate intensely, losing mass through Hawking radiation. The lightest ones would have evaporated by now. Any primordial black hole lighter than about 100 trillion kilograms would have completely radiated away its mass over the universe's 14 billion year lifetime. This evaporation sets a lower mass cutoff for detectable primordial black holes. Primordial black holes might explain other cosmic mysteries. Supermassive black holes at galaxy centers grew extremely quickly in the early universe. If primordial black holes served as seeds, the supermassive black holes could have started with substantial mass and accreted from there. The smallest primordial black holes face a dramatic fate that distinguishes them from all other black holes. A black hole with the mass of a small asteroid would measure smaller than a proton. No known natural process creates black holes this small. When the Large Hadron Collider began operations, some researchers predicted it might create microscopic black holes. These would not be dangerous. A micro black hole would evaporate essentially instantly, far too quickly to consume any appreciable matter. Experiments searched for characteristic signatures, but no convincing micro black hole signals appeared. A micro black hole with the mass of Mount Everest would completely evaporate in about 1 second. In the final microseconds, the black hole releases as much energy as a nuclear bomb. This terminal explosion should produce a characteristic burst of high-energy gamma rays and particles. Satellites and ground telescopes search for such bursts. Finding even one would provide the first observational evidence for Hawking radiation. But one recent cosmic event might have finally captured what scientists have sought for decades. In 2019, detectors captured an ultra-high energy neutrino, unlike anything seen before. One team proposed an extraordinary alternative. The neutrino came from a primordial black hole, exploding in its final moments. The mathematics align perfectly. A primordial black hole with specific initial mass, evaporating for billions of years, would reach its explosive finale at precisely the right moment to send that neutrino toward Earth. The interpretation remains controversial. The search intensifies as detector sensitivity improves. Every ultra-high energy neutrino gets analyzed for possible primordial origins. If terminal bursts occur frequently enough, someone somewhere will eventually catch one. That moment will mark a revolution in fundamental physics. The ultimate rare object might exist in a regime we cannot yet access. Perhaps it requires quantum gravity to form. Perhaps it appears only during brief moments in cosmic history. When we combine all these rare phenomena, we approach the ultimate limits of physical reality. The rarest things gradually reveal themselves as our tools improve. What seems impossible today becomes standard tomorrow. But some things might remain forever beyond detection limits imposed by fundamental physics. Physics imposes absolute boundaries on what can exist. The rarest thing in the universe ultimately might be the universe itself. One cosmos among potentially infinite possibilities. This one capable of producing observers, complexity, and extreme phenomena. The ultimate rarity becomes not specific objects, but the existence of any observers to contemplate them. The rarest thing might simply be now, this instant, this awareness that nature permits such wonder. We have journeyed from laboratories trapping individual anti-helium atoms to theoretical limits of physical law. We have explored stars made of quarks, black holes that evaporate, and particles that barely exist. We have seen that the universe operates not at median values, but at extremes. These extremes define reality's boundaries. They show what is possible, even if improbable. They demonstrate that nature is stranger than imagination. They prove that the rarest things, however unlikely, shape our cosmos in profound ways. The rarest thing might simply be the universe's infinite creativity, the ability of simple principles to generate endless complexity, the emergence of structure from chaos, consciousness from matter, and meaning from mechanism. In searching for the rarest things, we find ourselves. The rarest thing might simply be now, this instant, this awareness that nature permits such wonder. Thank you for joining this exploration. The universe awaits further investigation. If you are curious about the physics of true impossibility, watch this next on the fundamental speed limit that keeps us from breaking the universe.